Hello everyone. Let's wait for a few more minutes and then we will start our live session. Okay. Can someone confirm if I am audible?
Yes, sir.
Okay. Uh, are the slides visible?
Yes, sir.
Yes.
Okay. Thanks. Yeah. So we will start today's session. Good evening, everyone. My name is Arpit Bal, and I'm a PhD scholar at Department of Electrical Engineering, IIT Bombay, and I am the PMRF NPTEL TA for Digital IC Design course. And this is our live session number 8. Okay. So let me revisit what we have done so far. And yeah, so we will also have an additional live session at the end of the 12th week. So in that one we will do some important problems related to the various weeks that were covered earlier. Okay, and it will be a form of revision just before the actual exam. So last in last course that I took for digital circuits, it happened just after the completion of 12th week, but let's see how it happens this time. Okay, so in week 1 we covered few numericals related to VTH variation with VSB, that is taking body effect into consideration. We also did few numericals related to channel length modulation, and we did few questions related to drain current measurement using unified current equation. Okay, and we also saw how to figure out the region of operation of NMOS and PMOS. Then there were few numericals related to DIBL, that is another short channel effect, and we also did, in presence of DIBL and body effect, what happens to the VTH. That thing we observed in week 2. Then we did some questions related to junction capacitance and few more numericals related to PMOS. Week 3 we did some questions related to the trip point and VIH and VIL. So in today's session we will be revisiting one question related to VIH and VIL again. In week 4 we did questions related to noise margin and Elmore delay. Week 5 was related to power calculation and delay, as well as one question related to process variation. In week 6 we did questions related to delay, electrical effort, and how to design a CMOS schematic given a particular Boolean equation. Okay, then we did some questions related to capacitance calculation and gate sizing. Okay, then in week 7 we did questions related to path delay calculation and delay optimization. Okay, then few questions related to parasitic effort, logical effort, and electrical effort. So in week 8, that is today's session, what we will be doing is we will do one question on mirroring circuit. Okay, then some concepts related to pseudo-NMOS logic. Okay, so it can be put under the umbrella of special circuits. Okay, let us start today's session. So the first question is, so consider the Boolean function f ABCD is equal to ABC plus BC plus CA plus ABC bar, C bar whole bar. Okay, does the given function obey the mirroring property? Okay, so what do I mean by mirroring property is, let's say I have a pull down network, okay, and I have the pull up network for the CMOS. Okay, so usually how we do the CMOS circuit design is, we first start with the convenient one. Let's say we design the pull down network first and then take the complement, not exactly complement, if it is a dot then it changes to plus, and if it is in parallel it changes to series, and so on. Okay, and that's how we arrive at the pull up network from the pull down network. But the mirroring property, from mirroring property what I mean is, let's say I have designed the pull down network, can I have the same schematic as the pull down network in the pull up network as well? Okay, and it is found that there are some circuits which exhibit this property, okay, provided they follow this. If f ABCD equals to f bar ABCD, A bar B bar C bar D. Okay, if this condition is satisfied, then the function is going to obey the mirroring property. And what you can do is, once you are done with the pull down network, you can copy the same thing in the pull up network. Okay, and you will obtain the function that is needed for you. Okay, so what is the benefit with this thing? So as it was mentioned in the lecture, that let's say in the pull-up network we have a stack of 3 transistors, and in the pull-down network there is a stack of 2 transistors at max. Okay, so if I mirror the pull-down network in the pull-up network, then the let me add this. Okay, then what will happen in the pull-up network, the stack size also reduces to 2. Okay, so that's a benefit. And yeah, okay, so let us start with this question. So this is the function that is given to us, this is the equation that is given to us. Okay, let me simplify this a bit. F is equal to, let me take B common, so I will be left with AC plus C plus AC bar plus AC and whole bar of this. Okay, if I further simplify this, I have B common and I can take A common as well, so I will have C plus C bar plus C plus AC and whole bar of this. This implies it will be B, so C plus C bar will be 1, so A plus C. Okay, so I simplified the equation a bit to write it in this form. So one thing that you can do is, either you can go on verifying by taking the complements here and verifying this property, but that but that can be complicated. So instead what we will do is, we are going to make the truth table. Okay, so this is our input ABCD and this is my F. Okay, so this particular thing represents my F. Okay, so can someone tell me what will be the F values?
We don't need to take D.
Yeah, we don't need to.
There in the function.
Correct. We don't need to take D because D is not present in this function, but because the inputs are mentioned as A, B, C, D, so that's why I have mentioned D. So in the truth table, so you only need to observe the ABC part. Okay. Yeah, so can someone tell me what will be the answer? Means what will be the F value? So if A, B, C is 0, 0, 0, what will be my F?
1.
Okay. So can someone observe a pattern here?
0 and 1 has same ABC value. Similarly, 2 and 3 has same ABC value.
Okay. A bit more simpler. So like while evaluating the truth table, so if you can observe a pattern, then it becomes easier. So
similar to 3-bit ABC.
Yeah, right? Yes. It is similar to 3-bit ABC. You need not worry about the D part. But can I make this statement that if any 2 input is high, then f is going to be 0? Can I make this statement? So any 2 input out of A, B, C, if it is high, the f will be 0.
Yes, sir.
Okay. So because this one translates to AB plus BC plus AC. Okay. And this tells me that if either any of the 2 input at any time is high, okay, then the function is going to evaluate to 0. Okay, so at least 2 input. So let me mark those points as 0. So this is going to evaluate as 0. Okay, this will be 0, this is 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 0. Okay, so what will happen to the remaining inputs? It will be evaluated as 1. Okay, does everyone agree with this? Is there a doubt here? Okay. Okay, so you can write f as summation of 0, 1, 2, 3, 4, 5, 8 and 9. Okay. If f is this, then what will be my f bar? So you only need to observe the places which have 0 as the value for f. Okay, so this one, and these ones. Okay, so I can write f bar as 6, 7, 10, 11, 12, 13, 14, 15. Okay, now our condition to observe whether it satisfies the mirroring property or not is to check if the complement of the inputs are taken, then are we able to get f bar? Are we able to get this condition satisfied? F is equal to f bar. Okay, so let's see. So if it is 0, 0, 0, 0 and I'm complementing all the inputs, it will be 1, 1, 1, 1. Okay, it means my f bar 15 term should be covered. Okay, similarly for 1, if I take the complements, so 0, 0, 0, 1, it changes, like if you take the complement, it will be 1, 1, 1, 0. That is 14. Same thing you do with 2. Okay, and that will translate to 13, because this will go as 13. Okay, same thing you do with 3, and 3 will be 12. Okay, same thing with 4, it will be 11, 5 will be 10, 8 will be 7, and 9 will be 6. Okay, so because of this, it implies that this given Boolean function it obeys the mirroring property. Okay, is everyone clear with this question? Is there a doubt here? Okay, so can we proceed to the next question, or is there a doubt? Okay. Okay, so moving on to the next question. So consider this Boolean function, and does the given function obey the mirroring property? Okay, so let's drop D, and we will again repeat the same exercise. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1. Okay, so start telling me the values of f. So what is f?
One.
Okay.
Zero.
Okay.
Zero.
Okay.
One. Zero. One. One. Zero.
Okay. So was there any pattern here?
Odd ones detector.
Correct. Okay. So this is basically an odd ones detector. Okay. So what will be the equation for f? Okay, 0356. Okay, so what will be the equation for f bar?
1247.
Okay, can someone confirm if it obeys the mirroring property or not?
Yes.
Yes.
Okay, so 0 will be mapped to 7, 3 maps to 4, so wait, yeah, 3 maps to 4, then 5 maps to 2, and 6 maps to 1. Okay, and because of this it obeys the mirroring property. Okay, so any function that is given to you, so you can verify whether it obeys the mirroring property or not by using the truth table method. Okay, so is everyone clear with this, or is there any doubt? Okay, so yeah, sure. Okay, so if you are given with a Boolean function and you have to verify whether it obeys the mirroring property or not, so what you need to check is whether f of a, b, c, d, like input variables, equals f bar of a bar, b bar, c bar, d bar. Okay, so now what you need to do is first construct the truth table. okay, and get the values for f, okay. Then you figure out what is the equation for f, okay. Similarly, you figure out what is the equation for f bar, okay. Then you need to check this particular condition, okay. So what you do is, let's say this equation is f, okay. Let me go to the second one, okay. So let's say this equation is f is equal to summation of 0, 3, 5, 6, okay. So 0 can be represented like this in 3 bits, okay. So if I take the complement of 0, it becomes 1, 1, 1, right? That translates to 7, and 7 is present in the f bars equation. Similarly, you take 3 in f's equation, so 3 is 0, 1, 1, that translates to 1, 0, 0. 4 is present in f bars equation, okay. Similarly, if you take 5, so 1, 0, 1, 1, 0, 1, if you take the complement, it is 0, 1, 0, so 2 is present in f bar. Similarly, 6 is 1, 1, 0, if you take the complement, it will be 0, 0, 1. Because all these terms are already present in f bar, so our mirroring properties, that criteria is satisfied, and so like we can design a circuit which is like mirror of the either the pull down network or the pull up network based on the convenience.
Got it, sir. Thank
Okay,
you.
yeah. Is there any other question? Okay, and as you can observe, this is actually an even ones detector, okay. Whenever there is even number of 1, the function becomes 1, okay. Okay, moving on to the next question. Okay, so for a pseudo-NMOS inverter, if the VOL is equal to 0.05, what should be the ratio WN by WP? Assume that devices are of minimum length and short channel effect of velocity saturation exists, but other effects like Dibble and channel length modulation doesn't exist. Give your answer precise to 2 decimal places, that's fine. Do not make any approximation with respect to neglecting VOL by 2 with respect. Okay, so and assume VIH is equal to VDD. Okay, so let me draw a pseudo-NMOS inverter. Okay, and this is my input A. Okay, so first thing that I need to do is, let's figure out what is the region of operation. Okay, so what is VGS for the NMOS transistor? It is given as VDD. Okay. Yeah. So this is VDD. What is VDS?
Vout.
Yeah. So V out is VOL in this condition, right? So that is VOL. Okay. So the reason why we are taking it in VOL condition is because so assume A has a value which disconnects the NMOS completely. Then we don't have any issue because the current is going to flow through this path. So it can, so let's say there is a capacitor present here. So the maximum voltage that it can go to is VDD and there is no problem. Okay, but let's say A assumes a value, let's say VDD, then still the capacitor won't be able to discharge completely because the PMOS is going to be active. Okay, so we will take the limiting case for deciding the ratio of Wn by Wp. Okay, so it means we need to make the PMOS a bit weaker so that NMOS can successfully discharge the capacitor that is present at the output node. Okay, so that's why we take the limiting case VOL.
Is the answer 7?
No.
7 by 2.
Yeah, close to that.
3.50.
Sorry, can you repeat?
3.50. 7 by 2.
Yeah, it is close to that actually. 3.55 something. Yeah. Okay, so okay, let's do it step by step so that others can also. What is the region for NMOS? Linear. Okay. So for PMOS, what is VGS?
VDD.
Minus VDD. Okay. So what is VDS for PMOS?
VDD minus VOL.
VOL.
Yeah, VOL minus VDD. And the region is? Okay, so someone got 3.5, right? I guess you have considered region as saturation, is it, Ankit?
Velocity saturation.
Okay, yeah, it should be velocity saturation. Okay, let me. Okay, so what we are going to do is, so once we know the region of operation of the MOS transistors, we just need to equate the current. Okay, so we have Kn W by L VOL into VDD minus VTH minus VOL by 2 is equal to Kp Wp by L into VD sat P into VDD minus mod VTP minus VD sat P ka mod by 2. Okay, substituting the values. So Kn dash is 200. Okay, let me put the dash here. Is 200 micro and this is 100 micro. Okay, so 200 into Wn. Okay, let me bring the Wp to this side, so L will be cancelled into 0.05. VDD is 2 minus 0.4 minus 0.05 by 2 equals Kp dash is 100 into mod VD sat P is 0.4, 2 minus 0.4 minus 0.4 by 2. So from here, try to figure out what is Wn by Wp. Okay, so I request other students to try this as well and let me know. Okay, try to solve this and type the answer on the chat box. Okay. Okay. Yeah, it is actually 3.56. Okay, so the answer is 3 point, okay, let me just write it, 3.555, that is 3.56. Okay. Is everyone clear with this question, or is there any doubt? Okay, so I'll pause here for 1 minute so that okay. So from this, what can you tell about the strength of NMOS and PMOS?
NMOS is almost 4 times stronger than PMOS.
Correct. Okay.
Actually, 7 times if we consider mobility factors.
Okay. Yeah. Okay, so I hope this question is clear. So moving on to the next question. So okay, so Wn by Wp is already derived, so I would like you guys to try this question out. Okay, so I'll tell you the dimensions. Okay, so we'll use the same notation that was used during the lectures. Okay, so let's say this is beta and this is NMOS is beta and PMOS is alpha beta. Okay, and we have derived the relation that beta is equal to 1 minus alpha by 2. Okay, where alpha is equal to Wp by Wn. Okay, so what is my Wn and what is my Wp? So please try this out.
WP is 0.327.
Okay, and what is Wn?
1.163.
Okay, so what is the value of alpha that you got?
I just kept it as 1 by 3.56. I didn't calculate it.
Okay, yeah, that's fine. So basically earlier we calculated Wn by Wp. Here we just need to take the reciprocal of that, so 1 by 3.56. Okay, and then you need to figure out the value of beta. Okay, so what was the value of beta that you got?
1.16.
1.163.
Okay. Okay, so then you know the Wn, that is 1.163. And what is the Wp?
Alpha into beta.
0.327.
Okay, yeah, correct.
0.327.
Okay, so okay, I'm having some internet issues. Am I audible?
Yeah.
Okay. Yeah. Okay, so this is how the width of NMOS inverter and width of PMOS inverter is found. So I think the next question was related to width of PMOS. So we have already covered it in question number 4. Okay, so here you don't need to do much. So we have derived this relation in the class itself, and alpha is defined as Wp by Wn. Okay, in question number 3 we figured out what is Wn by Wp. Here you just take the reciprocal, you find out what is alpha, substitute the value of alpha in the equation for beta, and you will find out what is beta. So beta is the width of NMOS and alpha beta is the width of PMOS. Okay, so you have your Wp and Wn available with you. Okay, so moving on to the next question. Assume the Wn and Wp from question 4 and 5 so as to calculate the pull-up logical for a pseudo NMOS inverter. Okay, and yeah, don't need to bother about this part. Okay, so can someone tell me what will be the, so we are calculating for the GPU. Okay, so can someone tell me what should be the reference inverter's width?
For PMOS it will be same.
Okay,
0.3%.
correct. For NMOS?
NMOS will be half of it.
Yeah, so let me only write it as 0.327 by 2. Okay, so what is my CA equals to? Summation of these two, right? Okay, so what is my GPU? What is my CA in this case?
1.163C.
Correct.
GPU is 2.371.
Okay, approximately 2.37.
Okay.
So 0.327 by 2, and this is 1.163C. So the CC will get cancelled and you will be left with 2.37. Okay, so is everyone clear with this question, or is there a doubt? Okay, so moving on to the next question. So in this question, so we are given a figure, and it shows a dynamic footed inverter with a pull-up device. Okay, and the input changes from 0 to VDD. Okay, and a gain of -20 at the trip point. Okay, and the trip point is given as VDD by 2. Okay, and VDD equals 2. So VDD value was mentioned earlier. Okay, okay, so VDD is 2 volts. Okay, so our VM equals VDD by 2, that is 1. Okay, assume that all devices are short channel and the number written next to each device denotes the scaling factor concerning the minimum width. Okay. Okay, so determine the VIL of the inverter INV. Assume the noise margin approximate model for the calculation. So this is like repeating week 5's question, I guess. So can someone tell me what is the formula for VIL?
VM minus VDD by G in bracket. No, VM minus in bracket VM minus VDD by G.
No, that is for no, that's incorrect, I guess.
That is correct only, sir, for approximate model.
Okay, approximate model isn't VIL equals to VM plus VDD minus VM by G?
It is same. If you take minus common, it will get that formula.
Oh, okay. So you were mentioning the G above, is it?
Sorry, I didn't get you.
Sorry, what was the equation that you were mentioning? Can you repeat once again?
VM minus in bracket VM minus VDD.
Oh, okay.
So it will be, if you take minus out,
Yeah.
it will be
I didn't hear the VM part actually. Sorry.
Yeah, divided by G.
Yeah. This is correct.
Yeah.
Okay. So VM is your VDD by 2, that is 1 volt, minus this is 1, minus what is VDD? It is 2 volts, right? Divided by G, that is minus 20 in this question. So what is your VIL?
.9.
0.95.
Correct. Okay. Similarly, so we have to determine the VIH for the inverter INV. Okay. So what is the formula for VIH?
1.05.
VM minus VM by G.
Yeah. Okay, so VM is VDD by 2, that is 1, minus 1 by minus 20. It is 1.05. Okay, moving on to the next question. So in case the input IN rises to VDD, okay, let me put this in quotation, during the pre-charge phase itself and remains at VDD throughout the evaluation phase, then which of the following statements is or are true? Okay, give me 1 minute, I need to add a slide here. Okay, so is the first option correct, that there will be a static current discharge from VDD to ground from the PMOS transistors to the NMOS stack during the pre-charge phase? Okay, let me draw this. Okay, that diagram. Okay, so this is the diagram that we are talking about. Can I copy this somehow? Okay, so can someone answer? There will, so is the option, okay, A, B, C, D, is option A correct? There will be a static current discharge path from VDD to ground from the PMOS transistors to the NMOS stack during the pre-charge phase. Okay, and why not?
Because NMOS will be off, right?
Correct. So during the pre-charge phase, the NMOS is cut off as this clock is 0. Okay. So this is my evaluation phase. This is my pre-charge phase. This is my evaluation phase again. Okay. So during this pre-charge phase, so my NMOS is cut off. Okay. Because of this reason, we do not have any current path between from VDD to ground. Okay, so this option is not correct. Okay, so for option B, if the previous state of out was 0 volt, then out will continue to float at 0 volt in the pre-charge phase. Okay, and why not?
In this circuit, there will be no floating output. It will be either 0 or 1.
Okay. And why can you say this?
Sir, if it is like 1, the other PMOS will pull up, the one connected to inverter.
Okay. Okay.
And if it's 0, it will be pulled up by both NMOS.
Okay. Yeah, that is correct. Okay. So is option C correct?
Yes, sir.
Okay. And what is the reason behind that?
Because the inverter connected, PMOS connected to inverter will keep it high.
Correct. Okay. And what about option D?
PMOS will be cut off.
How? So which PMOS? When you say PMOS will be cut off, which one?
The one connected to clock.
The one connected to clock. Okay. If this is cut off, then okay. So this is during the evaluate phase. So in evaluate phase, the clock is high. Okay. So if the clock is high, okay, I agree that this will be cut off. But this is on, right?
Yes.
And what if my input is equal to 1?
Then there will be static current.
Correct. Okay. So this option can be true if input is equal to 1 condition is taken, because if input is equal to 1, okay, then this output is going to be 0, okay, and because of which this inverter will make this one 1, sorry, this output will be evaluated as 1 and this will be 0, and because of this PMOS transistor will turn on, and this is going to pull down the node. Okay, so this is going to form a discharge path from VDD to ground. Okay, so option D can be correct. Okay, so these were the questions that I planned for today's session. So let me briefly revisit what we did today. Okay, so the number of questions for today's sessions were less, but it covers most of the concepts that will be used for your this assignment. In the next week's tutorial, I'll put more questions, but yeah. So in today's session, what we did is we checked whether any function that is given to us, whether it satisfies the mirroring property or not. Okay, and we discussed like what is the benefit of having this mirroring property of any function. So then what we can do is we can simply just draw the NMOS and copy the same thing in the PMOS stack as well. Only thing is the inputs will be taken as the complemented form in the PMOS stack. Okay, and the benefit of this will be, let's say the number of stacking in NMOS is less than the number of PMOS, then we can copy the NMOS stack on the pull up network as well, so that the stacking gets reduced. Okay, so the first step, so we need to satisfy this criteria to call any given function as a function obeying mirroring property. Okay, so the step 1 is to construct the truth table. Okay, once you construct the truth table, step 2 is figuring out the equation for f and figuring out the equation for f bar. Okay, and step 3 is checking whether all the inputs that are present in the minterms equation, okay, whether the complements of that are present in the minterm equation for f bar. If it is present, then this condition is satisfied. Okay, and here we did an additional step. So whenever you are given a function, so try to figure out what special feature is present in that function. Like in this case, we tried to simplify it a bit, and we observed that if any two inputs is 1, then the function goes to 0. Okay, so this will help you in solving the question a bit quicker. In the next question, the question is similar to the previous one. So here the special thing that we observe is this is basically an even ones detector. So if you have even number of ones in A, B, C, then this is going to give you a 1. Okay, and we observed that it obeys the mirroring property as well. The next question was related to the Pseudo-NMOS inverter, and it was mentioned that if VOL is given to you as 0.05, so what should be the ratio of WN by WP? Okay, so here I mentioned why exactly VOL condition is taken into consideration, because that is the worst case scenario, and based on the worst case scenario always we take care of the design. So let's say you are from analog design background or something, then you must be knowing that we have a maximum input referred noise criteria. So that's the worst case, right? So similarly here also, so the worst case appears when the NMOS and PMOS both are conducting. That is when the input at the NMOS is applied as VDD. Okay, because in that condition the output cannot go down completely to 0. Okay, because the PMOS is also trying to compete with the NMOS to put a value on the capacitor. Okay, so what can be the minimum VOL value? So here the VOL value is already assigned to us, based on which we need to figure out how can we size the transistors appropriately so that this VOL condition is satisfied. Okay, we figure out the region of operation of the transistors. Okay, then we equate their currents. From there we figure out what is Wn by Wp. Okay, and we get this condition. Okay, next thing that we were supposed to find out is the size of individual NMOS and PMOS transistor in a unit sized pseudo-NMOS inverter. And from the lectures we have seen this formula, that beta equals to 1 by 1 minus alpha by 2, where beta is the width of NMOS and alpha beta is the width of PMOS. Okay, so alpha is basically Wp by Wn. We already figured out what is Wn by Wp. Just take the reciprocal of that and we will have alpha. Okay, so after finding the value of alpha, we just need to find the value of beta from this equation and then substitute the value of beta and alpha beta here to figure out what is Wn and Wp. Okay, so the fifth question was already covered in this one, that we were supposed to figure out what is Wp. Okay, so once we have the values for Wp and Wn, we need to figure out what is the pull up logical effort. Okay, the effort is missing here. Okay, so once we have this inverter with us, we just need to take the reference inverter. Okay, so in this case, whatever is the PMOS width, that will be the PMOS width because it's a pull-up logical effort. Okay, then to make it symmetric, so you need to ensure that the NMOS is width of PMOS in the reference inverter by 2. Okay, so then we figure out what is the CA in both the cases, and GPU is our CA of DUT by CA of reference inverter. That comes out to be 2.37. In the next question, so we saw a dynamic footed inverter and we were supposed to figure out what is the VIL. Okay, so VIL was nothing but your VM plus VDD minus VM by G, or this thing, and it turns out to be 0.95 volt. VM is the trip point that is given to us as VDD by 2. Okay, and VDD was 2 volts, so VM was 1. Next we were supposed to calculate what is the VIH of the inverter, and so VIH using the formula that we observed in week 5. So VIH is equal to VM minus VM by G, that is 1.05. Okay, so the last question was related to the pre-charge phase and the evaluation phase. So there will be no static current discharge from VDD to GND during the pre-charge phase because NMOS transistor is in cutoff. And second thing, if there is a previous state, there will be no floating observed here in the pre-charge path because of the presence of this PMOS inverter, this PMOS transistor, okay, so yeah. And in the previous state of out was 2, then out will be held at 2 in the pre-charge phase as well. Again, it's already present. Okay, and the last one, so there will be a static current discharge if, let's say, IN equals to 1, then these two will be conducting. Okay, and because of that reason, even this transistor will be turned on and there can be a path. Okay, so that's all for today's session. So if anyone has any doubt, then let me know, else we can wrap up today's session. So yeah,
I have a doubt in pseudo-inverter.
Sorry, pseudo-NMOS.
Pseudo-inverter.
Okay.
Sir, I was having doubt regarding pull-down reference inverter.
Okay.
You could clear that concept. So, if we take standard pseudo inverter with 2 by 3 and 4 by 3 sizes, I did
Okay.
not get the concept of how do we construct the reference inverter for pull down case.
Okay, for the pull down case, let's see how to proceed with this. Pull down, so reference. Oh, okay. So one thing here. So in the 2 by 3 and 4 by 3 case, right? So how did this one appear? So we actually consider, let's call this one as Ix.
Okay, okay.
Okay. So if you remember the derivation part, so what we did is, let me call this one Ix, let me call this IP, and this one In. So you have Ix plus IP is equal to In,
Yes.
right? And this was taken as beta, and this was taken as alpha beta,
Yes.
correct? So I have Ix plus, so IP, so can you tell me what will be IP?
Alpha beta times Ix by 2.
Okay. So not Ix, it is actually I, and I represents, okay.
Yes.
So what is my In?
Will be I.
Yeah. Okay. And we mentioned it here itself that this Ix should be equal to I. Correct?
But there will be current from PMOS also.
Yeah, there will be current from PMOS. But what I am saying is, this Ix that is present here, okay. So for figuring out the value of 2 by 3 and 4 by 3, what we did is we equated this Ix to I first.
Yes.
Right. And after that we proceeded with the calculation is equal to beta, and beta turned out to be 1 minus alpha by 2. Okay. And this exact value of 2 by 3 and 4 by 3 appears only if alpha is equal to 1 by 2.
Yes.
Correct? But in this thing, the assumption that we already took is that my Ix is equal to I.
Okay.
And because of this, it means that I need to construct my reference inverter which is exactly like this, because this current is also I.
Sir, Ix is I got it, sir. But
Yeah.
The IN will be different, no, sir.
No,
The current
IN
through
is the
NMOS.
current through this NMOS. Okay.
Yes, sir.
And what we are actually concerned about is the load current. Okay. So the load current of the design under test should be same as the load current of the reference inverter. And because in this case we started with this condition, with this consideration that my load current is equal to I, and after that I figured out the sizing of 2x3 and 4x3. So because of this reason, whenever I'm considering the pull down network, I'll take this as the reference inverter.
Okay, so got it.
Okay, yeah. Okay, is there any other question?
Can you explain the ninth question?
Ninth question. Okay, question numbering is wrong. Okay, which question? The last one?
Oh, yes, sir. I think the ninth question. To find out the GCA equal to
Yeah, this one.
yes, sir. Yes.
Okay. Should I explain this?
Yes, sir. Yes, sir.
Okay, so we already figured out, so by question number 4, so we have figured out what is going to be the dimension for WN and WP. Okay, so what we do is we just draw the DUT here, and whenever we are considering the capacitance for our input, the first thing that we need to do is we need to drop considering the PMOS, in particularly pseudo-NMOS inverter case, because there is no input connected to the PMOS. Okay, so my final capacitance CA for the DUT will be 1.163 C. Do you agree with this one?
Yes, sir.
Okay, so now the next thing that we need to do is to construct the reference inverter.
Okay, sir.
Okay, so for constructing the reference inverter, what we are going to do is, so when GPU is considered, so do you agree that the NMOS is going to be turned off completely?
Yes, sir.
So if the NMOS is going to be turned off completely, so will it mean that the load current directly flows through the PMOS only?
Yes, sir.
Okay, and because of this reason, the reference inverter that I will be considering for will have the same width of the PMOS. Okay, and because it will have the same width of the PMOS, so to construct the complete inverter, the NMOS width that I need to take should be half of the PMOS width.
Okay, sir.
Okay, and once I do that, so I just wrote whatever value was present here, 0.327 and 0.327 by 2.
Okay, sir.
Okay, and so the capacitance of the NMOS and PMOS in this case will be 0.327 plus 0.327 by 2.
Okay, sir.
Okay, so then my GPU in this case will be the ratio of this one divided by this one.
Okay, sir. Thank you, sir.
Okay, yeah. Okay, is there any other question? Okay, so if there are no more questions, then we will wrap up this session here. So the recorded lectures, this particular recording will be shared. I'll upload it by 8:30 or 8:45, and even the slides will be shared with you. So I think NPTEL team has already shared a sheet where it contains the link to the Google Drive folder where I upload the slides. So that will be also present. Yeah, so thanks everyone for joining, and I'll still be around here. If anyone has any doubt, then let me know. Yeah. Thanks. Hi Sumit, so do you want me to go through the problems that we covered today?
Yes, sir.
Okay. So today mostly we focused on the special functions circuit. Okay, and we had a few questions related to the mirroring property. So question 1 and 2 is mostly related to that mirroring property. So what the mirroring property says is, like, if the f a b c d equals the f bar of a bar b bar c bar d, okay, then what I can do is, while constructing a CMOS logic, so my pull down network, I can copy it in the same way as the pull up network. Means I can just replicate this here, or vice versa. Okay, so we are given this question to check whether this Boolean function, it obeys the mirroring property or not. Okay, so the first step, what we do is, so first thing, we try to simplify this function as much as possible, and we arrive at this equation, AB plus BC plus AC whole bar. Okay, then we construct the truth table. Okay, after constructing the truth table, we see at what positions f1 f is becoming 1, and based on that we write the equation for f in terms of the min terms. Similarly, we do the same thing for f bar. So for f bar, you just need to see at what location of f it becomes 0. Okay, and that thing you can write as the equation. And next thing that we see is, if f bar contains all the complements of the inputs that are present in f, then this criteria will be satisfied, right? So let me give one example. So because 0 is present in f, so I must have 1 1 1 1, that is all complements of 0 in f bar, which is present here. Similarly, for 1 it is 14, for 2 it is 13, 3 it is 12, 4 it is 11, 5 it is 10, 8 it is 7, 9 it is 6. Because all the inputs are present, so this property is satisfied and it obeys the mirroring property. Okay, same thing. So it was a different question. So question number 2 is also for finding out whether it obeys the mirroring property or not. Next, we did a question on pseudo-NMOS inverter. Okay, so we are given a pseudo-NMOS inverter whose VOL is given to us. We need to figure out what is the WN by WP. Okay, and we had to assume VIH is equal to VDD. From these conditions, we figure out what is the region of operation of transistors. Okay, then we equate the transistor currents. After equating the transistor currents, we figure out what is WN by WP from those equations. After figuring out what is WN by WP, we were supposed to figure out what is the size of WN. Okay, and from the lectures we know that beta equals to 1 by 1 minus alpha by 2, where beta is the width of NMOS and alpha beta is the width of PMOS, where alpha represents WP by WN. As we already know WN by WP, so we figure out alpha from there by taking the reciprocal. Then by putting the value of alpha here, we find out what is beta. Okay, from there, so beta corresponds to WN and alpha beta corresponds to WP. Okay, then the next, okay, so in this question we were supposed to figure out what is WP, and we have already figured it out in question number 4. Okay, so question number 5 is already done. In question 6 we were supposed to figure out what is the pull-up logical effort. Okay, so we have the circuit given to us from question number 3. We figured out the WP and WN values. For pull-up, we just need to copy the PMOS that is present in the pull-up network. Okay, and for getting the NMOS value, you just divide the width of PMOS by 2. Okay, then you figure out the CA value in the design under test. Okay, So here we can see that the A signal is connected to NMOS only and not to the PMOS. So our CA is 1.163C. From the reference inverter, we can find the CA as 0.327 plus 0.327 by 2. That represents the NMOS and PMOS gate capacitance. Okay, then you take the ratio of these two, that will give you the logical effort. Okay, so for the next set of questions, this was the image that was given to us, and we were supposed to figure out the VIH and VIL. Okay, and this is the equation that we saw in week 5, where we were doing questions related to noise margin and VIL, VIH. You just put the values here. Vm is the trip point that is given to us VDD by 2, and VDD in our case was 2 volts, so it becomes 1. Correct, and you figure out what is VIL. Similarly, VIH, we directly use the formula, and the gain is given to us as minus 20. So this is the value for VIH. Okay, then the question related to the pre-charge and the evaluation phase, and we know that there won't be any static current discharge from VDD to ground when the pre-charge phase is on. So the first statement is wrong. Second statement is wrong because you can see, so we have this PMOS present, which will avoid any kind of floating gate condition. Okay, and because of that PMOS itself, so we have our output held at 2 volt in the pre-charge phase. And the last one, so there will be a discharge path. If the input is 1 and clock is 1, then this path will be conducting, and there will be a path from VDD to ground for the case T. Okay, so the recording of today's lecture will be available on the YouTube channel, so you can check it there. Okay, and these slides will also be uploaded on the Google Drive. Okay, yeah, so is there any question that you want? So
sorry to interrupt you, I went late.
Okay,
So can you show me slides from the start as a quick
Sure.
sum?
So this was the first question where we were supposed to figure out whether this given equation follows the mirroring property or not. Question 2 was also same, but the equation was different.
So can I take the screenshot of this one?
Yeah, actually it will be available to you. Like, I'll upload it after this session ends. I'll upload it in the drive.
Okay.
Okay, yeah. And so you can also check the recording. It will be available here. Give me 1 minute.
Actually, I am not completely explored the session, so I didn't know that how to
Oh,
do these
okay.
problem solving recordings and all that.
Okay, no problem. Like, next week also we will have this session, and so same time from 6 o'clock. So
it's average this day.
yeah, it is every Tuesday.
Every Tuesday.
Yeah, so this is the so every Tuesday we have this live session that will start sharp at 6. So, and the recording of the previous sessions are available on that YouTube channel.
Yes.
And the slides, I think, will are already shared by the NPTEL team, right? They must have shared a folder.
I guess so, yeah. Lecture slides are there.
Okay. Okay, so yeah, you can go through them. Okay.
Can you give me idea about question 10, 11 and 12, how figure and diagram?
This one?
Yes, sir.
Okay, so what we need to find out is the VIL and VIH. Okay, and this is something that was done in week 5, I guess. So there you can directly put the values and get the VIL and VIH for 10 and 11. In 12 we were asked to like figure out whether these statements that are mentioned here are correct or not. Okay, and so first thing, like in the pre-charge phase, so if you see, okay, so in the pre-charge phase the clock is low, so because of that reason this will be disconnected. So there is no possibility that there will be a path between VDD and ground. So first statement is wrong. Second, if the previous state is like some 0 volt, then the output is not going to float because we have a transistor, the PMOS is present here. So it will bring this value to some known value. Okay. Third thing, if the previous hello. Okay. Yeah. So third thing is like if the previous state was 2 volt, then the output will be held at 2 volt in the pre-charge phase. It is again because of that PMOS that is present. Next thing, that if so the next question is during evaluate phase, so will there be a static current discharge from VDD to ground? The answer is yes, if input is 1 and clock is 1. So clock will be 1 in evaluate phase, so clock is 1, input is 1, so there will be a path from here to here. And if PMOS is turned on, so there will be a path from VDD to ground. So even condition D is possible. Okay. Yeah. Okay, so you can join the next session, means the next Tuesday onwards also. So that's
Now I'm aware, I believe.
okay. Yeah, sure. Okay. Yeah, thanks.